Hi, and welcome to Codex. Our speaker today is Dardo Goyeneche, who is an associate professor at the Universidad de Antofagasta, leading the quantum information group. Dr. Goyeneche works in various facets of quantum information theory. Today, he will tell us about mutually unbiased frames. Take it away, Dardo.
Okay, Emily, thanks. Thank you very much for letting me present our work here. So this is a collaboration with two students from my groups, Fabian Caro and Victor Gonzalez. And I will talk about middle unbiased frames. So first, let me fix the notation. So I will consider the direct notation that we use in quantum mechanics. So elements in a Hilbert space are denoted by kets. With this symbol, we denote Berg, which is an operator that if you add this operator on a ket, then you have a bracket, which is a complex number. And if you do this operation, then you have a rank 1 projector. So let me start with the most common notion of unbiasedness, which is for orthonormal bases. So two orthonormal bases are mutually unbiased if this relation is satisfied. And a set of 10 orthonormal bases are mutually unbiased when they are pairwise unbiased. So we know that there are at most d+1 mutually unbiased bases in dimension d, and we also know that this upper bound is reached in every prime dimension and also in every prime power dimension. But in any other composite dimension, for instance, in dimension 6, the problem is still open. So nobody knows if 7 mutually unbiased bases exist, and even more, nobody knows if 4 mutually unbiased exist. So everybody knows that 3 exist, but nothing else. And for instance, this is a set of 3 mutually unbiased bases in dimension 2, and here we have a representation in the block sphere or Poincare sphere for mathematicians. So these two-dimensional vectors in the Hilbert space are associated to a real three-dimensional vector in the surface of the block sphere. And here vectors that are anti-parallel are orthogonal in the Hilbert space. So here we have 3 bases. Another remarkable constellation are the SIC-POVM. And a SIC-POVM is a set of d-squared normalized vectors defined by this condition. So the overlap, the square absolute value of the overlap between all the elements is a constant. And this is the representation for a two-dimensional set in the block sphere. So SIC-POVMs are regular simplices in the block sphere representation. In higher dimension, you can also have a hypersphere, a block hypersphere, but the problem is that the surface of this hypersphere is not entirely composed by pure states. So the surface is much larger than the set of pure states. So it is simple to define regular simplices in these hyperspheres, but the problem is how to find the way to rotate a regular simplex in such a way that all the vectors in the surface are rank 1 projectors. So for these two problems, the mutually unbiased basis in dimension 6 and the SIC-POVM problem, there is a prize, an award given by the Gdańsk University, and this reveals that these two problems are quite important in information theory. Another example of importance are the regular simplices, which is a set of d+1 vectors, normalized vectors in CD, such that this equation holds. So, for instance, this is an example of a regular simplex in dimension 2. And let me introduce frames which are defined by this equation. So if you have n vectors and n pure states in a d-dimensional complex Hilbert space, you have a frame is there exists constant, real constant A and B, such that this inequality holds. When A is equal to B, then the frame is tight. And if these two constants are equal to 1, then we have a tight frame, which is called Parseval frame. And now another relevant set of the equiangular type frame, which generalized some already previously shown structures. So a set of n vectors defined in dimension d are an equiangular type frame if this equation holds. So if the absolute square value of the overlap is equal for all of them, but not any angle. So you have to satisfy this specific angle, because otherwise you have equiangular lines, but not equiangular type frames. This is a very interesting conjecture posed by Massificus, which says that if you have an equiangular type frame composed by n vectors in a complex Hilbert space of dimension d, then one of the following quantities divides the product of the other two. And this conjecture holds for all the solutions known. For instance, if you consider SIC-POVMs, the element of vectors is d squared, and you can see that you can rearrange the numbers in such a way that you get an integral number here. For regular simplex, you have the same integral number. And the same holds for equiangular type frame arising from Hadamard matrices, where this is the relation between the dimension and the number of vectors. And this is an integral number because the Hadamard matrices exist in order which is multiple of 4. There is an exception in dimension 2, but this does not apply here because this construction that I mean here works for square dimensions. For instance, a very simple way to construct a equiangular type frame from Hadamard matrices is to consider an Hermitian symmetric real Hadamard matrix, which has a constant Mayan diagonal, and then you can shift and rescale this matrix in such a way that you get the ground matrix of an equiangular type frames composed by d vectors in dimension n with this relation. And also another important ingredient are the positive operator value measure. This is the most general kind of measurements allowed in quantum mechanics. So a set of n operators forms a POVM if all of them are positive semi-infinite and they sum up to the identity. And if you consider the Gauss rule, which connects quantum state and measurement with the probability of the outcomes that you get in the lab, then these two conditions translate to these two, which is just saying that probabilities are real and non-negative, and they sum up to 1. So this is the most general kind of measurement that you can define in quantum mechanics. And interestingly, these rank 1 POVM are equivalent to unit norm type frames. Well, now we have reached the point that we present the middle-unbiased structures. So all of these unbiased structures shown here are already known. So I already defined the middle-unbiased basis, but there is also a notion of unbiasedness for simplices, for equiangular type frame, and for POVM. So now the idea is to generalize all of this to any frame. So not necessarily frames composed by types. Structure composed by type frames. A particularly interesting detail is that SIC-POVM can be seen as a set of multi-unbiased frames. So let me introduce this notion. So two frames in a Hilbert space of dimension d are unbiased if this relation holds, and a set of frames are mutually unbiased if they are pairwise unbiased. So let me show you now the solution to the general solution to the simplest way to define neutral unbiased frame, which is in dimension 2, in the complex single space of dimension 2, and each frame is composed by two vectors. So suppose that we have a frame given in the block field representation. So we have the red vector and the gray vector. These are our two vectors, and then we construct two cones, yes, with any amplitude that we wish, with the restriction that they have to intersect. Because if they do not intersect, then we cannot define an unbiased frame with a given angle. So once they intersect, you take these two vectors, which lie and they are the intersection of the cones, and then these two vectors form a frame which is unbiased to the other. And now an interesting question arises, is whether equiangular lines, whether neutral unbiased frames are just collections of equiangular lines. And the point is that they are something else. Because suppose that we have 4 neutral unbiased frames in C3, and these frames suppose that are arranged in rows. So it is true that every column defines an equiangular line. But however, any other combination, like this one, also forms an equiangular line. So these neutral unbiased frames are a sort of combination of equiangular lines with combinatorics. So it's not just a set of equiangular lines. Okay, now let's describe a bit the overlap in this neutral unbiased frame, which we denote with the letter C. So suppose that we construct the elements, the projections associated to these directions with a risk scale in such a way that they sum up to the identity. So if we have rank 1 POVMs, then this constant is fixed to 1 over D, just like the case of neutral unbiased space in any dimension. But in general, if they are frames which are not tight, so if they are not POVM, then this constant is lower bounded and upper bounded by these numbers, with these two numbers AL and BL are just the frame bounds. So we have to take the maximal of all the lower bounds of the frame and the minimal of the upper bound of the frame. And equivalently to the above, if one has a frame that is tight, then the overlap is 1 over 2. Now let us consider a matrix approach to study the neutral unbiased frames problem. So let's consider that we have m neutral unbiased frames arranged in columns of these matrices. So therefore, we have these relations where the square absolute value of all entries of this matrix K, this matrices K, are equal to C, because this is the overlap of the vectors. And also, due to the normalization of the vectors, this condition holds. But this point of view does not simplify the problem. So it is very hard to construct m matrices for a given value of C. So this is too hard. So in order to try to find some solution, we have to assume something else. And let's have the following assumptions. So first, we assume that these matrices are normal. So they commute with the echelons. And also we assume these other relations. So all of them commute. And also all of them commute with the addition operators, and they commute with the odd matrix K. So the advantage of these assumptions is that all matrices are diagonalized by a single unitary matrix. So once we fix this unitary matrix, the problem reduced to study suitable spectrum of these matrices and K that produce structure matrices K. When I say structure matrices, I mean some prescribed absolute value of entries, which is the geometry of the problem. And just to show that this is not a trivial choice, if you consider the unitary matrix equal to the identity, then you can only get one orthonormal basis, and you cannot have a mutual invasive frame. So it is crucial to have a good choice of this unitary U in order to find something interesting. So the key question is what choices of U are relevant? And we don't fully understand this yet, so this is an ongoing work. But today we will restrict our attention to the case of circular matrices. So let's assume that U is circular. And I think this is the simplest possible choice one can have, in the sense that there is a simple formula that connects the entries of the circular matrix with the spectrum. So, assuming this, we have these small results, which says that if we have a set of circular matrices that form n mutual invasive frame, composed by d vectors each in dimension d, so these are square matrices, then the normalized vectors defined by the eigenvalues of these matrices form n equiangular lines in CD, with the same overlap than the mutual invasive frame. So the question is whether these assumptions are too restrictive, and not at all, because one can define mutual basis here. For instance, if you consider prime dimensions, you can have n equal to d mutual invasive basis, which is almost a maximal set. And this is so because the eigenvector basis, the basis of the following of these operators, can be written in a circular form, with the exception of this one, which is diagonalized by the Fourier transformation. For instance, in dimension 3, these are 3 mutually invasive bases, and we clearly see that they are circular. So the remaining basis is Fourier basis. Now let me show you a solution, the most general solution of the case of 2 modes in dimension 2, assuming this circular form. This approach can be solved analytically. So two frames having this form where the vectors are in columns are mu if and only if this condition holds, where this is the value of the overlap. This formula for C holds when alpha, beta, theta, and eta are different from these numbers. So, for instance, here there is a very nice fact because we can merge in the same place SIC-POVMs on 2 mutually invasive bases. So when theta is equal to 0 or pi, sorry. Theta is equal to 0 or pi, and eta is equal to pi over 4 or 3 pi over 4, and beta equal to 0, we have 2 mu's, and when alpha is equal to beta and theta minus theta satisfies this relation, then we have a SIC-POVM. And it is interesting here that the SIC-POVM belongs to this family, but the mu's are exceptional sets. They are here. These parameters do not satisfy this equation. We don't understand very well why this is so, but this is the property that we observe. Now let's try to go a bit further and assume something else. And we will consider that M is equal to T. So the number of frames that we consider is equal to the dimension of the Hilbert space. And we also consider that the vectors, the vector associated to the eigenvalues, defining the spectrum of these matrices, form a circular matrix. Because we have M matrices here, each of them has associated a vector formed by the eigenvalues, but all of them are unknown, and we want to fix them. So to simplify the problem, let's consider that all of them form a circular matrix. So we just have to restrict our attention to the eigenvalues of the tensor. And the question is whether this is too restricted to have solutions. And the answer is that not so much, because we can have a Weyl-Heisenberg covariant SIC-POVM. I'm curious because the standard projector says that Weyl-Heisenberg SIC-POVM exists in every dimension, but this is only known in a finite set of dimensions. And this is the form where you can get the entire set of an orbit of a fiducial state in the Weyl-Heisenberg group. And why these two simple assumptions that we had concerning circular matrices imply the standard conjecture? This is simple because, well, first let me show this property that the first row of circular matrix is connected to the vector of eigenvalues via the Fourier transform, but we can translate rows to columns in this very simple way. So we have to apply two permutations. This is the Fourier matrix. The square of the Fourier matrix is a permutation. So if you apply this permutation to the columns and then to the rows, you see that when you have vectors in rows, you have vectors in columns here. So it's equivalent to talk about rows and columns. So if we consider the same frame, the third frame, elements are related by a shift because this is a circular matrix. But also, when you go from one matrix to the other, given that eigenvalues of this matrix are a shift of this one, then we have that the columns of this matrix, or row, which is equivalent, are related by the sit operation. Okay. Why this is so? Because a shift in eigenvalues translate into a sit operation into the rows, because it's the Fourier transform of the shift. So this way we can see the SIC-POVM as a collection of d-mutual invasive frames in any dimension where the standard conjecture goes. So the only problem is that they have to form a frame. So they have to be linearly independent. So these matrices have to be invertible, or what is the same. They should not have vanishing entries in the eigenvalues. So note that eigenvalues, the vector composed by the eigenvalues of M is also a fiducial state, because this is just the Fourier transform of a column, of a row, of the matrix. And the Fourier transform is an element of the Clifford group. And if you apply the Clifford group, an element of the Clifford group to a fiducial state, then you get another fiducial state. So the question now is whether fiducial state can have vanishing entries. And the answer is yes, and this was noticed many years ago by Sauner in his thesis in dimension 3, but also very recently by Marcus Grassel in other dimensions, 26, 28, 62, 98, and 228. So now, if we want to avoid this problem of the vanishing entries, we can take for instance, one of these fiducial states with vanishing entries and apply an element of the Clifford group. So in order to get another fiducial with non-vanishing entries. So therefore, in this way, any Weyl-Heisenberg covariant SIC-POVM can be essentially seen as a set of D nearly invasive frames in dimension D. So this sounds very reasonable, but the problem is that we don't have yet a proof of this fact. So we are trying to prove it. As another property, these matrices forming the SIC-POVM sometimes can be Hermitian. In order to have Hermitian matrices, we require to have a real set of eigenvalues. So if you have a real fiducial state in dimension D, then all of these matrices will be Hermitian because all the eigenvectors of these matrices is just the shift of the previous one. And about the existence of real fiducial states, we know that there is a conjecture that they exist in every dimension of this form. And this conjecture is supported by 18 existing real fiducials, being the highest in dimension 19, 1,603. So it's a very high dimension. And note that all of these dimensions are off. Let me show you an explicit family of Hermitian matrices. So in dimension 3, there exists a family of real fiducial states, continued family, and these matrices from SIC-POVM, these are Hermitian. These are the numbers 0, 1, and 2. So this is the simplest example that we know. So what about the even dimensions? So are there fiducial states, real fiducial states in even dimensions? So fiducial state with respect to the standard Weyl-Heisenberg group. And the question is no. The answer is no. And the proof is extremely simple, because we start to realize that if you consider a real fiducial state in an even dimension, and if you make numerical simulations, you will always get that some entries of the Green matrix will be 0. So under an orbit of the Weyl-Heisenberg group, you get some zeros, and for instance, it is simple to realize that this overlap is always 0 in any dimension. So this result is new as far as we know. And now let's talk about the free parameters that we have in a fiducial state, because in principle, a priori, one has no idea about the structure of the suitable vectors that generate the SIC-POVM. So in principle, one has two D minus 2 free parameters to fix in order to determine a fiducial state. But now we will show that this number can be reduced a priori. So in any dimension. So if you have a fiducial state, phi with respect to the standard Weyl-Heisenberg group, then the following holds. So look here that we have in the left-hand side, we have the amplitudes in the canonical basis of the fiducial state. And here we have some phases. Some phases having this symmetry. So in every dimension D, we have this number of phases, which is D minus 1 over 2 on the flow function. And also we have the phases of the fiducial state, because this equation also only involves the amplitude. So we have an additional number of D minus 1 phases, complex phases. So this is the total number of parameters that you want us to fix in order to determine the fiducial state. So this result was proven by using metal massive point of view. But after finishing our proof, we realized that if you consider the discrete version of the Weyl-Heisenberg theorem, you can also find the same. And this result is not new, but it's unpublished as far as we know. I will talk to you later about that. And now let me show you some numerical results, very interesting numerical results found by Chris Fudge some years ago. So he was studying numerically the free parameters in the SIC-POVMs in dimensions 9, 10, 11, and 12. And he found that in odd dimension, it seems that this is the number of parameters that you have to fix. And in even dimension, this is the number. And these are our numbers. In odd dimension, look here, compare this number with this one. So this Fudge has one less than us. But here, in the even case, we have one less. And now let me mention this unbiased result related to our equation to reduce the number of free parameters. Because Junger in 2008 found this result in a very simple way, which is fully equivalent to our result. Note that here, this is the overlap between two elements of the SIC-POVM. So we have a phase with this amplitude. So this is the action of the SIC operator. We have this relation, but this is nothing else than the Fourier transform of this element. And this is exactly this relation. And now let's talk about entropic uncertainty relations. So if we consider the quadratic range entropy and probabilities coming from quantum mechanics, when you consider maximal set of mutual invasive bases, then the following uncertainty relations hold. And this inequality is saturated for the minimum filter state, of course, and of course, if and only if this inequality holds. And it is very interesting that fiducial states are minimum uncertain state in every prime dimension. So if you put a fiducial state here, you saturate this inequality. But these are not the full, fiducials are not the full set of states that saturate this inequality. And now let's show this result, which shows that if you have a d-dimensional quantum state satisfying this equation, the symmetry that we found, and suppose that you consider the columns of any unitary matrix belonging to the Clifford group, and you calculate its probabilities, then you find this relation. And this is exactly what you need to have the saturation of these entropic principles. So it's a generalization in the sense that you can consider not only mutual invasive basis, but any basis given by the columns of an element of Clifford group. So this is the generalization of the result. So if you have a d-dimensional quantum state satisfying this property, in particular fiducial state, then it is a minimum uncertain state with respect to every set of d+1 orthonormal bases formed by the columns of d+1 elements of the Clifford group. So in particular, you can consider also d+1 mutual invasive bases in prime dimension. Okay, to conclude, we introduced the notion of mutual unbiased frames, right? And we applied this notion to study some particular constellations, the SIC-POVMs, and we found that the fiducial state have roughly 3D over 2 free parameters, which is much smaller than the 2D minus 2 that once one previously knew. And we have proven that real fiducial state under the Weyl-Heisenberg group do not exist in any even dimension. And finally, we derived some entropic uncertainty principles saturated by a class of quantum states that contain all existing fiducial states in any dimension. So that's all. Many thanks for your attention.